Hello and welcome back to Math 301, Introduction to Combinatorics at CSU. We're going to be talking about division in combinatorics today, and the last time we talked about addition, subtraction, and multiplication, and now we'll see where division comes in. So let's start by counting some rocks. The first version of the division principle says that if A things are grouped evenly into collections of size B, then there are A divided by B collections. Here's 12 rocks sorted into groups of size 3, and there's 1, 2, 3, 4 groups. So this picture illustrates that 12 divided by 3 equals 4. But the second way we can use division, the second division principle in combinatorics, is that if A things are grouped evenly into C collections, then the size of each collection is A divided by C. So here, the number of collections is 4, and the number of things in each collection is 3, so we also have 12 divided by 4 equals 3. Again, simple sounding principles, but very, very highly applicable in combinatorics, and the trick is to figure out what are your rocks, what are your groups, and what are your sizes in a given combinatorics problem. One strategy for using the division principle is actually a quite advanced strategy in combinatorics called overcounting. You want to overcount by some factor. Say you count each rock twice and then divide by 2. So that's the strategy we want to do. Count everything a certain number of times, because doing that might actually be an easier thing to count at first, and then you can just divide by how much you overcounted. So let's see some examples of this. How many anagrams of math have the M appearing before the A? We talked about counting anagrams of math in a previous video, and we talked about how rearrangements in general are counted by a factorial. And this goes along with the multiplication principle. There's 4 ways to choose the first letter of your anagram. Once you've chosen that, there's 3 letters left to choose for the second possibility, and then 2 letters left for the third letter, and so on. And so we have 4 factorial possibilities, or 24 anagrams. But we want to count how many have the M appearing before the A. I claim that we overcounted by a factor of 2, and that's because we can match up the ones that have M before A with the ones that have A before M by just switching the M and A in that word. And so actually there's twice as many that have any possibility as there are that just have the M before the A. And so we can just take 24 divided by 2 and we get our answer. There are 12. Let's draw this out really explicitly for this example. Here's all the pairs that I mentioned on the previous page, math and AMTH, and then MTAH and ATMH. Each of these pairs, you just take the M and A and switch them. And notice on this table, all 24 possibilities of the way of rearranging the letters in math appear, and we've grouped them into pairs of 2, and each of these groups have exactly one of the things that we're trying to count. And so we take the 24 and we divide by 2, there's 12 groups, that's how many we're looking for. So when you don't care about the order of the M and A, you just divide by the number of ways of rearranging the M and A. Let's do another example. Say we go back to the handshake problem. 5 people walk into a room and every pair of people shakes hands. How many handshakes occurred? So again, remember we draw the people as dots or nodes and we connect them by edges, and so each edge is a handshake. Now, one way to do it is just count the actual edges, and we saw many ways of doing this in the first video, but we can also say, well, a handshake is one person shaking hands with another. There's 5 ways to choose the first person, and then 4 ways to choose who they shake hands with. Now, that looks like there should be 5 times 4 or 20 handshakes, but we've counted each edge here twice, because if this person, C, shakes hands with E, well then E also shook hands with C. So counting C and then E, and also counting E and then C, means we counted each edge exactly twice, and so we actually overcounted by a factor of 2. So we have to divide by 2. A shaking hands with B is the same as B shaking hands with A, so again, we divide by 2 and we get 10. So here's another example that's not just dividing by 2, it's a little more complicated. How many necklaces can you make with beads labeled 1, 2, 3, 4, 5, and 6? This means, mathematically, how many ways can you arrange the numbers 1 through 6 around a circle, like ordered around the circle, up to rotation? Now what up to rotation means is if I take this arrangement of beads and I rotate it 1 step to the right, so the 5 becomes here and the 1 goes here and so on, that's the same necklace. So you don't want to count the same necklace a different time just because you rotated it, it just rotated around your neck a little bit. So the question is, how many cyclic orderings of these beads are there? So let's start with all the orderings. So we know the number of ways of rearranging 6 things is 6 factorial, because we can choose in 6 ways what goes at the top, and then times 5, times 4, times 3, times 2, times 1 for the number of choices of what to put in each circle. That's not considering rotation. But that's an overcount. We overcounted each arrangement by 6 because you can rotate exactly 6 times before you get back to the original arrangement. And so actually we counted each necklace 6 times when we overcounted. And so the total is actually 6 factorial divided by 6, which is 5 factorial, or 120 possible necklaces. Now, here's the guideline translating between English and math. When you see up to in a problem, that definitely means divide. When it says up to rotation, you divide by the number of rotations. When you say up to symmetry, there's going to be some kind of symmetry and you have to divide by it. So we'll see this as we go on later in the course as well. So now you try. How many necklaces can you make out of the letters in twists? And notice that there are 2 T's, and those are identical. You can't tell the difference between the 2 T beads, say. So this is almost like making necklaces out of 5 beads up to similarity of the 2 T's, where you cannot tell the difference between those 2 T's, so there's some kind of extra symmetry you might need to divide by. So that's all for today, and I'll see you next time.